All right. So let me begin with this thing that many of you may already know, but I just we go through this the so-called polarization. So we start with so suppose so you have just some vector space V, a complex vector space. And you'll see that the complex that I is crucial in this whole argument. And okay, then a map from V cross V so you take an element of x comma y in V cross V to, let's say, I don't want to use inner product notation, but it's basically the same idea. In C is said to be sesquilinear. Welcome back. Okay. How many of you know this word? How many of you do not know this word? Okay. Sesqui means really 1.5. Okay. So it is a function of two arguments. It is 1.5 linear means it is kind of linear in the first variable and half linear in the second variable. That meaning if you fix one variable, so okay, let me put it this way. I'll put it if summation alpha xi summation beta j xj should be, if it is linear in both variables, then you'll be able to pull out the constants. But the half linearity refers to this statement. It like the inner product, the classical example is the inner product. It is conjugate linear in the second variable and linear in the first variable. Okay. Such a thing is a sesquilinear form. And given such a sesquilinear form, the associated quadratic form is is qx equal to xx. Okay. So So the polarization identity says that, see, it is clear that if you know the quadratic, the sesquilinear form, then from that you know what the quadratic form is. The polarization identity tells you that if you know, given a quadratic form, if you know that it came from a sesquilinear form, you can find what the sesquilinear form is. So the identity is so this refers to okay. So what does it say? It says that if I take x in a product y, sorry, not in a product. See, typically I will use it for xi eta equal to x xi eta, where x is a linear operator and xi eta are vectors. I should have started with xi eta here, but anyway, you know what I mean. Okay, so it says that you can recapture this from the sesquilinear form, and so let me just let me write down the proof and then I'll write the equation down. Okay, so notice that if you look at q of x plus y, so you can just expand the thing out, right? You can write x plus y, comma x plus y, and then expand the whole thing out. Then what you'll find is that this will be qx. No, I know I required is it clear that this is okay? Okay, so let me assume that if the sesquilinear form is Hermitian, it's Hermitian symmetry, i.e. xy is yx bar. Okay, so I only want to look at this kind of sesquilinear form. Okay. Then what you get qx plus qy plus xy plus yx, which by the assumption is the same as xy plus xy bar. So which is plus 2 times the real part of xy. So you replace y by iy now and find that q of x plus iy equal to qx. Note that q of iy is the same as qy because the I and the I bar will yeah, I and I bar will come out and then kill one another. plus twice real part of xiy, which is the same as minus this I will come out as minus I, right? So minus twice real part of I xy. So from this we find that q of x plus y minus q of x minus y, all this is really high school algebra, is 4 times, no, 2 times the real part of xy plus no, there's IY here. No, wait, so let me do this right. Okay, so 4 times real part of xy. No IY, sorry. Sorry, I'm making a mess here. What I wanted to say was, let's look at q of x minus y. Replace y by minus y. Then what you'll get will be qx plus qy minus twice real part of xy. So that if you subtract qx plus y minus qx minus y, you get 4 times real part of xy. Now do the same thing with y. In this equation, substitute iy for y. And you get q of x plus iy minus q of x minus iy is 4 times the real part of xiy. So just for fun, let me throw in an I here. Okay, now notice the following thing. So what is this? This is 4i real part minus 4i real part of ixy. See, box xiy is minus I box xy. That's all I've used. Okay, now I want you to observe that if you take any z equals u plus iv, and if you look at minus I times real part of I times z, I claim that this is, what is this? This is minus I times a real part of iu plus iu minus v. Equal to what am I?
I times
imaginary power.
No, what do I want to do? I want to get so I times imaginary part of z. So what we see from all this is that if you add all these, now if I add these two equations, okay, then what I have is 4 real part of z and then plus 4 times I imaginary part of z, which is just 4z. The right side will just give you 4 times box xy. Right? So this will tell you that 4 times box xy is qx plus y I'll write it in a different order. Minus, we added these, right? So plus I times q of x plus iy minus q of x minus y minus iq x minus iy. The exact formula is not important. What is important is that you can recapture the sesquilinear form as a linear combination of the quadratic form and corresponding vectors, associated vectors. But I will write this same formula in a slightly more clever fashion and economical fashion. I'll write this as 1/4 summation j equals 1 to 0 to 3 of I power j q of x plus I power j y. I'm just writing this in shorthand, but the important thing is that you can recapture the sesquilinear form from the quadratic form. Okay, so now see, I want to read out some important and useful consequences of this, which is okay, so what do I want to say? Corollary. Let x and be of h. Okay, by the way, for notational consistency, I will start writing these funny symbols for Hilbert spaces and subsets. You'll see, because if I write just h, then I would, natural notation for a subspace will be m. Whereas for us, m is going to be typically a one-Neumann algebra. It's going to be an algebra of operators. So the straight letters will stand for collection of operators, just to keep our notation clear. And so these funny vectors is for collection of vectors. These funny fonts. Okay. So subspace a subspace of this I will denote by something like this. Okay. Okay. Then 1. X is 0 if and only if x psi eta is 0 for all psi eta in H if and only if x psi is 0 for all psi in H. Okay, but I should kind of pause. I hadn't noticed this thing before. We used Hermitian symmetry of that thing. So a priori, this one knows only for self-adjointings. Right? So for the moment, let us say for
And so here Hilbert's is a whole complex.
there are always complex Hilbert spaces. Let me assume x equals extra for a moment. Because only then if this x psi eta, if I define that as box of psi eta, that is the Hermitian sesquilinear form. I use that Hermitian, I think one can maybe get on that. Huh?
Qx plus y minus q of x minus y equals to real part of xy. That part you have used Hermitian.
No, I have used Hermitian, but I'm wondering if okay, it's okay. So in general, so I'll say x is self-adjoint. Okay, I've already assumed x is self-adjoint. No, so let me not say this is the assumption. So this is only the proof. So in the proof, I'll sort of get down to the proof. So okay, so what should I say here? If and only if x I is I. Huh? Is real. Okay, so the proof, so we'll do it by notice that Z will be a weight and if you take the unique Cartesian decomposition where x, y are self-adjoint, right? Then I want to observe that the sesquilinear form of see one way is clear. So first observe, so I'm proving one. So first I observe that into this way is obvious. Because you can take, by definition of the adjoint and Hermitian symmetry of the inner product. Okay. So if I take a general Z and if I write it, if I take its Cartesian decomposition, what we note is that xi equals the real part of zzi and yzi is the imaginary part of the same thing. That is, in more than one sense, it makes sense to call x the real part of z and y the real part of z, imaginary part of z. Okay, so now I say, therefore z, see, so let me call this z. Clearly z is 0 if and only if z xi eta is 0 for all xi and eta. Right? So let me start with z equals 0 if and only if z xi eta is 0 for all xi and eta. So, and then some so I want to conclude that z xi is 0. If and only if z xi is 0, I want to say. But this implies clearly, see, this is equivalent to z star equals 0. This is equivalent to what do I want to say? The conjugate of this. What is the conjugate of this? Eta z xi. Okay, so what I see is that if and only if why should I say all this? Both of them are 0 if and only if the real and imaginary parts are 0. One is z plus z star by 2, one is z minus z star by 2. So if and only if x equals y equals 0. But for self-adjoint x and y, we have shown that okay, so this is equivalent to x xi eta equals y xi eta equals 0 for all xi eta. This is true for any operator. Being 0 is the same as the sesquilinear form being 0. But for self-adjoints, this is equivalent to the quadratic form being 0. Right? And so we get what we want. This is equivalent to the same thing with xi equals eta. Okay, so we see that something is 0 precisely when its quadratic form is 0. Now this, it is important that we are in the complex case. It is because this statement is not true in the real case. They are not true. One is false in real Hilbert spaces. Because in R2 you can look at the mapping B of R2, which is identifiable with M2 of R. You look at this matrix. This matrix, if you think about it, is just the rotation by an angle of pi by 2 in R2. It sends E1 to E2 and sends E2 to minus E1. Right? And it is clear that if you take the rotation, you take any vector, you rotate it by 90 and then take an product, you will get 0. So this operator will have quadratic form identically 0. But it is not the 0 operator. So then quadratic form, if I call this A, or quadratic form of R is 0, but R is not 0. Okay. And now if you go to the polar decomposition, the Cartesian decomposition, Z equals X plus Iy for a general Z. We know that the quadratic form also will have real parts as the quadratic form of X and the imaginary part will be the quadratic form of Y. And so for the thing to be real is precisely when the imaginary part is 0, that means Y should be 0. So there is the proof of the second part that something is self-adjoint precisely when its quadratic form is real. Okay, so that takes care of that. Okay, now we come to start getting serious. So, theorem. Let A in B of H. And the following are required. A is positive. That is, I spell out what I mean in the definition. And all notions of positivity are the same. But I'm just here I want to be pedantic and take this definition of positivity. A is self-adjoint and spectrum of A is contained in R plus. I'll interchangeably write SP and sigma. So you must have noticed me already doing that one this morning. Being self-adjoint and having positive spectrum is equivalent to requiring that there exists B positive such that A equals B squared. We've seen this already. In fact, we know that such a positive square root is unique. And let me say, there exists a T in P of H K for some K such that A equals T star T. and finally what is the final condition in the quadratic form a xi okay. So for the proof I think 1, 2. This we've already done. 2 implies 3 is a triviality. I can take k equal to h and t equal to a power half and t equal to b, and 3 implies 4 is also trivial. Because if you take t star t is I xi, there is going to be norm t xi square. So we only have to prove this converse relation. So we have to assume that A has a positive quadratic form and deduce that it is self-adjoint and has positive spectrum. If the quadratic form is positive, then it's certainly real. So a 4 clearly implies that A is Hermitian. And we had proved last time that any self-adjoint, just as any real function, can be written as a difference of two positive functions which are disjointly supported. That corresponds to the statement that A can be written as A plus minus A minus with A plus or minus positive. A positive meaning they are self-adjoint with positive spectrum. Okay. But then notice the following thing. On one hand, with more, not just positive, they are actually disjointly supported. I can even write the other way by taking adjoints of this equation, because everything is self-adjoint. It will tell me that A minus A plus is also 0, because A plus and A minus is self-adjoint. Okay, this will imply that A minus A minus okay, I never read longer things. So what is this? This is A minus times no A is minus A minus cube. Actually, A minus cube, not A power minus 3, the cube of A minus. Okay, so what does this say? This says that on the other hand, if you take A minus A minus xi, that is the same as A minus xi, because A minus is self-adjoint, which by the assumed positivity of the quadratic form of A is non-negative. On the other hand, minus of A minus cube clearly has spectrum negative. Right, contained in R minus, or A minus cube is positive. So it will have positive quadratic form. So minus A minus cube will have minus A minus cube xi must be less than or equal to 0. So the only conclusion is that the cube of A minus has 0 quadratic form. Therefore, this A minus must be 0. A minus cube must be 0. But A minus is self-adjoint, and therefore its norm is its spectral radius. This says that the spectrum of A minus cube is only 0, so the spectrum of A minus is also 0. Right? Because it is of self-adjointness. And so we conclude finally that therefore A minus is 0. i.e. A equals A plus is positive. See, this is the first time that we have proved something really non-commutative in spirit. So far we are talking about the commutative C-stars that are generated by self-adjoint and making all kinds of statements about commutative C-star algebras which could be identified with continuous functional algebras. And so we could use the continuous commutative theory to work with them. This is the first instance where we've proved a theorem which is really non-commutative in spirit. See, in this T, it doesn't even make sense to say T commutes with A. Even if K equal to H, T may not commute with A. So our proving that anything of the form x star x is positive, even if x is not self-adjoint. So you are out of the commutative theory. If x is not normal, x star x is not living in a commutative C-star algebra. So this is the first time where we actually used the commutative theory efficiently to prove something about non-commutative situation, about non-commutative C-star algebra. All this is true for any C-star algebra contained in B of H, but that is neither here nor there. Okay. Now let me get to the next class. So among the class of all operators, we've singled out self-adjoints and normals as important subclasses. We haven't done much with normal operators as yet. Yeah.
So how do you decompose self-adjoint operator is sum of positive and minus?
See, you went here when I proved that fact that if you look at the C-star algebra generated by X, where x is self-adjoint. That is isomorphic to the continuous functions on the spectrum of that x, which is a subset of the real line. So the algebra is isomorphic to the algebra of continuous functions on a compact subset of the line, where self-adjointness corresponds to real valued function. So I am saying a real valued function can be written as f plus minus f minus, where f plus and f minus are positive functions whose supports are disjoint. And I am just transporting that via that functional calculus back to the C star A to conclude this thing. Okay, so the next thing we want to look at, the important class I want to single attention on is the following thing. So you know this fact that if you take, suppose M is a closed subspace. One of the first theorems you prove in Hilbert space theory is that if you have a closed subspace in Hilbert space, and if you take any vector z in the Hilbert space, it can be decomposed as z can be written as x plus y, where x is in M and y is in M top. Okay, I keep making the notational mistake, but I should write xi eta where we're talking about vectors. So now the point is that the mapping that sends z to x, that is the orthogonal projection from onto M, and so this is denoted by the orthogonal projection onto M. Okay. And one verifies easily. I leave the proof verification to you. Pm satisfies Pm equals Pm squared equals Pm star. To say it is squared means that it is a projection. But that will happen even if you take an oblique projection. Pm equals Pm star corresponds to the fact that it is a perpendicular projection. And conversely, if E equals E squared equals E star, mu it, and if M equal to range V, then E equal to Pm. Thus, orthogonal projections are the geometric notion of an orthogonal projection is algebraically captured by the requirement that the operator is idempotent and self-adjoint. Okay. So, all right. So, actually later when we talk, I have mentioned monomial algebra, but if M is a monomial algebra contained in B of H, Neumann algebra. We will use the notation P of M equal to the set of all such objects, all projections in M, so that E equals E squared equals E star. Then you can talk about this, a projection being in a one-Neumann algebra. Okay. It turns out the study of projections is very centrally and intimately connected with the study of one-Neumann algebra. Okay, so let me continue with this. And so I should have also observed that, see, this and norm E less than equal to 1. Actually, it is equal to 1 unless it is 0. Because vectors in M it will fix. So if it has fixed vectors and if it has non-zero fixed vectors, then the norm is at least 1. And the fact that norm z squared equals norm x squared plus norm y squared will tell you that norm of Pm is less than equal to 1. Okay, so all these are all, any projection is self-adjoint and contractive. Okay. Okay. So here is silly little lemma. So let E1, E2, or I will call it EF, in PF M. For this, you can think of you can take M as B of H. It doesn't matter. Take some two projections, any two projections. Then I want to say the following are equivalent. EF equals 0. FE equals 0. E plus F belongs to P of M. If you let us think of M equals B of H actually. We proved it already in B of H and it's certainly true for any sub also. So in B of H, what is, so let, suppose E equal to P sub M and F equal to P sub N. What does EF equal to 0 mean? It means that E must kill everything in the range of F. What is the range of F? It is just N. So this means that E must kill N. En is 0, or that N is contained. Who are the vectors that killed by E? Exactly the things in the orthogonal complement of M. Right? And this is the corresponding thing. Fm is 0 or M is contained in N path. Both of them just say that M and N are orthogonal. And if E plus F is supposed to be a projection, this must have norm less than or equal to 1. That means E xi xi plus F xi xi. Let's prove 3 implies 1. See, what's the quickest way to see it? This is actually, you can see that this is the projection onto M plus N. If M and N are orthogonal subspaces, then M plus N will be a closed subspace, and the projection onto that will be the sum of the two projections. Or you can see straight away that you look at, see, E xi xi plus F xi xi I wanted to go an algebraic proof, but never mind. Say that E plus F EF plus F, see, this must say that E plus F squared must be equal to E plus F. So what will that say? That will say EF plus FE must be 0. And if you see what EF plus FE see, EF plus FE is 0. Let us multiply this on
Then E plus F whole square is E square plus F square. And E plus F whole square.
That is how I got this equation.
This is projection.
If I am given 3, using the fact that E plus F is idempotent, I deduce this equation. Now from this I want to conclude that EF is 0. EF, E F E plus
EF equals to F. EF star equals to F.
yeah.
We have to prove EF equals to F with this condition.
I have proved that EF equals 0.
If EF equals to F, there will be 2 EF equals to 0.
Huh?
If we can prove that EF equals to F,
How do I know that EF equals FE? FE plus FE is 0. Okay, If this is true, multiply this equation on the right by E. Then you get EFE plus FE equals 0. Right? That will mean that EFE equals minus FE. But EFE is positive. This is what is this? This is EF times FE. FE is the adjoint of EF. So anything on the form Z star Z is positive, so this is positive. So this means that FE is negative. Right? But that means in particular that FE must be self-adjoint. If FE is self-adjoint, that means FE is equal to EF. If FE equals EF, then if F and E commute, then they is the same as
That means 2EF plus 2EF.
is the same as minus FEF if you wish. The same thing here, it's positive one way, the other way it is negative. And so the whole thing must be 0. But this thing is some Z star Z. So Z must be 0. So there's just some algebraic fiddling around. But the geometric inside is exactly this. In terms of subspaces, it says just that. Okay. Okay. So we're now heading to this important theorem called the polar decomposition theorem. So before that, just a little notation. So you take an X and B of H. Actually, this can be operated between two different Hilbert spaces also. Then one can talk about the so-called left support actually no, before I get into that, maybe I should do just some the lattice structure of PM. Okay, so I want to observe that PM P of B of H that is the collection of all projections. I want to say is a complete lattice. That means I'm saying, so what is the order? When I say lattice, that means I have some order. So I should say okay, so I should tell you what the order is. So before that, let me just ask you to note one obvious little thing. For EF in here, to say that E is less than or equal to F. So I will use this notation to mean that the difference is positive. Right? So given, we'll write one operator smaller than another operator only if the difference is self-adjoint and positive. Typically we'll write it only for self-adjoint operators. Okay, now this, when E and F are projections, this is equivalent to saying that E, think of them in terms, suppose this is PM and this is PN. See, so we're talking about, what does this say? This means that E xi is less than or equal to F xi. Okay. But what is E xi xi? If E is a projection, E is E squared. So I can write this, I can double this E, and the D is self-adjoint, I can take the D over to the other side. So this is just norm of E xi squared. Less than or equal to right? And notice that norm E xi equal to norm xi if and only if, so what does it say? Norm E xi squared equals norm xi squared. Norm E xi squared is E xi xi. So you're saying which is equivalent to saying that 1 minus E xi xi is 0. But notice that this one I'll write rather than 1 minus E, sometimes I'll think of it as E per, because there is nothing, that is nothing but the projection onto the orthogonal complement of the range of E. Right? So this happens if and only if xi is in E xi equal, xi is in range of E. That is E xi equals xi. Okay. This is the same as norm of 1 minus E xi squared. So that will be 0 precisely, but 1 minus E xi is 0. Right. So a projection will attain its norm at some vector only if that vector is in the range. Okay, so in particular, this will say that if we take any xi in the range of E, norm E xi will be equal to norm xi. That means norm f xi should also be equal to norm xi because f is a contraction. So if f xi equals, so E xi equals xi means f xi equals xi. That means this says that M is contained in it. So the order that you put on projections is the natural one. If one space is smaller than another space, then you think of the associated projection as being a smaller projection. And this is the same as saying EF equal to E. If you first project onto the bigger space and then project onto the smaller space, that is the same as projecting straightway down to the smaller space. Okay, so here are some, these are some so this is the order structure on the projection, collection of all projections. I want to say it is a lattice. In fact, this says it is I should even say ortho-complementary. That means there is this perp notion among the projections, which reverses the order. For every E, there is an E perp, and E is smaller than F precisely when E perp is bigger than F perp. Okay. So, the only thing, the remaining thing is this thing. So, what is meant by complete lattice? It is, that means it is a partially ordered set where every subset has a least upper bound, every non-empty subset has a least upper bound and a greatest lower bound. Right? But if you go to the level of subspaces, it's not surprising at all, right? If you take a collection of subspaces, P sub Mi, any collection of projections look and they're in bijection with subspaces. So what would if somebody wants to be bigger than all of this, what would it mean to say that Pm sup of this is Pm means what? It means Pm must be bigger than each of this and must be the smallest thing which is bigger than all of these. That means given a collection of closed subspaces, I'm saying there is the smallest closed subspace which contains all of them. And what is there? There is just one natural one, right? So M equal to the closure of this you take the union of Mi and you take the closed span of that. That will be Pm. So that is the sup. And similarly the inf. If you have sup, then you also have inf, because you can go to the orthogonal complement and take the sup and do some De Morgan kind of nonsense. And you prove the other thing, that inf, or equivalently you can say inf of Pmi equal to P of intersection over all I Mi. Then you give a collection of subspaces. I want to say there is the largest subspace contained in all of them. And that largest subspace is clearly the intersection. Okay. Okay, so now let me get back to the people that started writing and took it away. Oh no, so let me get back to here. So I talk about, so given an x in, so you look at the set of all P in P of B of H. Take projections in H with the property that x equal to xp. That makes sense, right? X is an operator from H to K. Look at all those things in H such that x equal to xp. See, what does this mean? This means that, so this is some collection of projections in B of H. And as such, they must have a supremum. Right? Yeah, I fix x in B of HK. Then this supremum certainly makes sense. Okay.
So X is an operator of H.
From H to K. That is what I have said. B of HK. You have two Hilbert spaces and X is an operator from H to K. And then I can talk about this supremum. See, what does this mean? This means really that this is the same as saying that x times 1 minus p is 0. Okay. This says that the kernel of x must contain the kernel of p. So what I am doing is I am taking all those projections whose kernel is contained in the kernel of, so this is equal to, so first take all Q and the range Q contained in kernel X. That means XQ is 0. Take all those things, those are the P perps. Now taking the soup of P, soup of a bunch of P's is the same as you take the inf of all the P perps and then take the perp of that. So this is the ortho the complementation coming in the natural way. Okay, so this is so inf of this perp. Okay. So this is called the that means whenever I have x, so if I call this projection x times, so I call this R of x, so called right support of x. That is, outside of that it is 0, or on the orthogonal complement of that it is 0. That is what it means to call it a right support. And similarly, one can also look at, you write things the other way. Similarly, one talks about Lx equal to sup of all p in p of b of k such that x equals px. And this is a left support. Okay, before we start using all these things, I just finished today with something that I'm sure we've discussed before. I just quickly ask you to recall this fact. If x is in b of h, again it can be h to k. I want to say that the range of x perp. You remember this thing? I've done this surely I've done it before. Kernel of x star. Right? So a little exercise for you is now to see that or you can also write the other way. The kernel of if you take the kernel of x perp, I should say x star. Let me change x and x star. If you take kernel x perp, that will be the perp of this. So it will be the range of x star closure. Okay. So the exercise for you is, now you look at this thing that I've written here. Look at this description of the right support of a inf of something perp. So, and similarly you write the thing and you will be able to, from that, deduce that the left support of x is the projection onto so it is the smallest projection such that you can multiply x on the left without changing anything. That means P must fix any vector in the range of X. Right? If P, this L, I mean, L must fix any vector in the range of X. And because the fixed point of L is a closed subspace, so L must fix the closure of the range of X. So this is the projection onto range X closure. And similarly, R of X actually equals L of X star. Equal to projection onto L of X star is projection onto range X star closure. Okay. Huh?
Cardinal of X bar.
Or I'll take kernel of X perp as kernel perp of X, so I don't have to write extra brackets. Right? So you get comfortable with these notions, and notice that if X is self-adjoint, and we will define this as just S of X and call it the support of X. There is no left or right when it's self-adjoint. So what is it? It is the projection. It has two descriptions. It can be thought of with the projection onto the kernel perp of X, or it can be thought of with a projection onto range X closure. Okay, I think the stage is set now for the polar decomposition, which is our next item of the agenda.